make a brief recap of what we are doing, and we can make the recap by looking at the web page. Let me share it. Okay, here we are. Let's see if we can share the screen, the right screen. Let me just check, because I cannot see on the phone. Can you see the web page?
No.
Okay, thank you. Just 1 second, I try to understand what's going on. Let me see. Let me share the screen. Okay. Now let me see if, okay, but this is not the screen I wanted to share. So let's see. Okay, here we are. Now, we are talking about deductive method for assessing water resources. And in particular, we just talked about rainfall runoff modeling on Monday and the linear reservoir. And the linear reservoir, I think it's a nice example of a mathematical model for simulating the rainfall runoff transformation. And you remember that we started from the mass balance equation, the one that you see here. This is a mass balance equation. Where PT is rainfall, QT is river flow. Remember that this is PT is net rainfall. So we have to assume that if there is some losses, they are already subtracted. And of course, because we need to get net rainfall, because this is the input to the mass balance equation. And therefore, we have to take into account the actual mass of water entering into the catchment. And then there is the QT is the river flow. PT is, sorry, I forgot to say that. It's net rainfall multiplied by the area of the catchment. So it's volume of net rainfall per unit time. So we got this equation, and then we took a energy balance equation, which we introduced by taking an empirical linear relationship. Okay, and then we made this computation, and we got to the final expression, which is this one for whatever rainfall p tau. So here you can plug in whatever function. Just remember that what I said. So this is an integral which you may compute analytically if p tau is nicely behaved. So if p tau lends itself to analytical integration, you can compute this integral analytically. Otherwise, if p tau is not well behaved, what you have to do is to substitute the integral with the summation. And therefore, we make what is called the numerical integration. So today, I also would like to talk about the differences. What is analytical integration? What is numerical integration? And it's very easy, by the way, the numerical integration, because what you have to do is just to make a summation that is extended at time intervals between 0 and t, the extremes of integration that you see here. But as I said, if p tau is nicely behaved, for instance, if rainfall is constant, we can analytically integrate it. And here we made the example of the analytical integration with constant rainfall, which leads to obtaining what you see in the far right term. It's the expression for the river flow with constant rainfall P as a function of time, okay? And this function is generally depicted here in this figure. Very good. Now, we introduced some assumptions then, and let me just summarize on the on the graphic blackboard with a very simplified scheme of what we are doing here. And I already did it last time, but let me make it again. Let me share now the graphic blackboard. So what we are doing here is to represent the catchment as a tank. As you may remember, we said this is the conceptual scheme that we use, okay? And basically, we assume that we have a PT coming in, PT. We have a QT going out, and then we have some water into it, WT. Okay, so this is the scheme that we did. I just would like to point out that we assume that this tank has an infinite depth. So we don't have any overflow here. So whatever is the value of WT accumulating, it may be very high, but there is no overflow. So it's a tank whose walls are indefinitely high. Okay, and this assumption is implicitly introduced if we don't put in the mathematical equation any condition that says that there is a max value for WT. So given the way we have written the equations, it's implicitly assumed that there is no limit to WT. And this also tells you an important thing. When we build a model, when we make a mathematical representation, whatever it is, there are explicit assumptions, which are conditions that must be respected in order to ensure that the equations can be written in that way. So in our case, the explicit assumption that we have written is that, let me change the color in red. There is one explicit assumption, which is WT can be written as the product of a constant K times QT. So this is a clear assumption because we assume that there is a linear relationship between the volume and the river flow. And this is something that we have to state because it's conditioning the validity of the model. But then there are some implicit consequences of using this equation together with the mass balance equation. And the implicit consequences are that WT has no limit. And this implicit consequence is something that it's important to be taken into account because you get a perception of how your model is simulating the catchment. And I mean, it's not an assumption. Strictly speaking, as I said, the assumption is something that conditions the validity of your equations. The fact that WT is unlimited is a consequence of the assumptions. It's not really. We can say that we assume let's say in a very simplified way. We could say we assume that WT is unlimited, but the correct way to say it is that a consequence, an effect of the fact that we write the linear reservoir by using these two equations is that WT is unlimited. And this is important because, as I said, you get a picture of how your model works. Perfect. Now, I told you that in some cases we cannot write, unless the rainfall is nicely behaved, we cannot write QT has an analytical function of PT. We cannot do that. We can do that only under other simplifying assumptions, like constant rainfall. This is another assumption that we may introduce. And then we can write this equation in this way because we have seen that we have derived the analytical form of the function f. But if we cannot make an analytical computation, I said we have to make a numerical integration. What does this mean? As I said, it's simply a summation, because let me write the second equation. The second equation is pt minus qt is equal to the derivative of wt in the t. Okay, and this means that I can write this equation in this way. I can say that w, the increment of wt, which is infinitesimal, is equal to what? pt minus qt, and this is multiplied by dt. I can write this equation in this way. And therefore, at each time step, I can compute through this equation the change in volume into the tank depending on rainfall and river flow. Okay, so when I go to numerical integration, as you know from other courses, the infinitesimal increments are to be substituted with finite differences. So I can write delta wt is equal to pt minus qt, which multiplies delta t. And then it becomes very easy to apply the model, because let's suppose that you work with daily time steps. So you simulate the dynamics of your catchment, you simulate the mass balance equation in your catchment every day. You adopt a delta t that is 1 day, which means that every day you have a value for rainfall, and you have to compute every day what? The value of W and the value of QT. Okay, so what we could say is, let's start from time 0, and let me write this equation here. So delta W0, which means that, or let's say not 0, let's say 1, because let's start from 1, because it's easier, no? Delta W1, which means that in the first day, I have an increment of what? I have an increment of W. And this increment can be computed simply by, I rewrite the equation, I write P1, which I know because I know the rainfall in that day. It's my input data, minus Q1 times delta T. Now, what does this mean? That if I assume that I have a volume W0 from which I start, which may be 0 or maybe whatever value you want to start from, then I can compute W1 has what? W0 plus W1. It is very easy. But then you may say, but I don't know Q. In this equation here, you may say, I don't know Q. But Q can be computed by using this equation here. Okay, and precisely, let me rewrite this equation in this way. QT is equal to WT divided by K. Okay, and then how can I compute in this case then Q1? Let me change the color because otherwise it becomes messy. So how can I compute this Q1, which is unknown here? Okay, I have to take this equation and write, for instance, that Q1 is equal to W0 divided by K. It is very easy. And if W0 is 0, okay, Q1 is 0. And then I can move forward and say delta W2 is equal to PD2 minus Q2 delta T. And what is Q2? Q2 is W1 divided by K. Okay, it is very easy. It is a simple summation. But there is one thing that you may say. You may say, look, you computed Q1, which means river flow at day 1 has a function of storage W at day 0, which means the previous storage. You may say, why didn't you apply a different equation? So I could have said that Q1 is computed at the end of the day. So I could have said that Q1 is equal to W1 divided by K. Of course, we don't know W1, and it's an iteration, and therefore I may say that I have to introduce another assumption, like let me assume that at the first step I compute the storage W1 is computed by ignoring Q1. So what I mean to say is that when you make a numerical integration and you work with finite differences, in this case 1 day time step, you have two choices when you have to compute Q1. You may compute it by as a function of the previous storage W0, or you may, by introducing a complication, compute it as a function of the current storage. This is a complication. And it's a complication because what you should do is to devise a different way of structuring this equation. I will show you. And what is the reason of this reasoning that I am making? Of course, if you take one choice or the other choice, you take a slightly different result. Why? Because there is an approximation in the numerical integration. This is what I wanted to tell you. When you work with finite differences rather than with analytical integration, it is easier, especially today with these powerful computers that we have, but there is a numerical approximation which is related to choosing whether the variables, the unknowns, should be taken their value at the previous time step or the current time step. Okay, and this is, of course, what we call numerical approximation. This numerical approximation, of course, it is more relevant if you have large time steps, because with large time steps, W makes big changes. So suppose that the time step is 1 year, and then W has big changes. So the numerical approximation becomes really important, okay? And therefore we have to adopt, we may adopt several different numerical approximation methods. Now, let me open another graphic window because I want to make this clear. This is something that is not explained in detail in my web pages because it's not something that I ask at the exam. It's something related to practical application. And as I said, let me make it clearer, and let me copy just 1 second. Let me write again the equation that we have to apply. So I said the color is blue, that's fine. Delta W1 is equal to, I said, P1 minus Q1 times delta T, okay? And then I said first option. So let me change the color. First option, 1. Q1 is equal to W0 divided by K. I take W at the previous time step. So the unknowns, because here in this equation I have an unknown, which is Q. The unknowns are fixed by taking their value at the previous time step. This is called Euler method. Euler method of numerical integration. Okay, second option. Second option is Q1 is equal to W1 divided by K. We don't know W1, and the W1, it is to be computed with this equation. W1 is equal to W0 plus delta W1. But delta W1 is unknown because it's unknown Q1. How can we do that? How can we solve this problem? Very easy. Let's apply this equation and let me rewrite it. Let's apply this equation in this way. Delta W1 is equal to P1 minus Q hat 1. What is Q hat? Q hat is a trial value. You guess it. You guess it, and then once that you know W1, you can compute this equation. You can compute W1 through this equation, and then you can, through W1, compute again Q1, and then you compare your trial value Q at 1, Q at 1 with Q1 that you computed. Is it, are they comparable? Are they close? If they are close, you are fine. If they are not close, it means that your initial guess was wrong. And then you have to repeat the process. You have to make another iteration by making another guess. And for instance, the second guess may be precisely the Q1 that you computed. And this is iterative. In fact, several numerical approximation methods are iterative and are called, these iterative methods are called Runge-Kutta methods. There are several iterative methods, several Runge-Kutta methods, which differ on the way the initial value of the unknown is guessed. So the message that I would like to convey is, you cannot perform an analytical integration, no problem. You can make a numerical integration. We have several methods to do that. Numerical integrations involve an approximation, no problem. And you can decide what kind of approximation you want to introduce. The Euler method is very easy. If you want to introduce an iterative method, it's a little bit more complicated. We will make now an exercise today to show an application of the Euler method. Okay, do you have any questions on this, let's say, first half hour where I wanted to introduce numerical methods and make clear that the linear reservoir can be solved analytically and numerically. Last time we talked about analytical solution. Today, in this half hour, we have introduced the numerical solution. And then later on, in about 15 minutes from now, I will ask you to open an RStudio window, and then together we will make an application of the Euler method. Any question? Okay, now let me go back to the web page, and so let me share the screen and let me share this. And let me, before we make the exercise, let me make an extension of the linear reservoir. The linear reservoir is a simple application of a conceptual scheme, and the conceptual scheme is simply a tank with walls, we said, of unlimited height. And in the same way, we could use a different scheme, like, for instance, the one that you see here, which is taken from Wikipedia. This one, you see, it's a tank, but here you have several discharges. You don't have a bottom discharge, but we introduce, in this case, 3 holes in the walls. And these discharges, subsequent discharges, are activated when the water level reaches each of them. So you have an initial storage. If it starts raining, you have an initial storage with no flow, no river flow. And then when the water level gets to the level of the first of the lower discharge, you start having some flow. And this is a model that, being structured in this way, would be nonlinear. Why? And let's reason by intuition. The intuition is that if you have an initial storage with no flow, it means that at the beginning you have some rain with no flow. So it's like an ineffective rain. At a certain point, you start seeing some flow, which means that there is a threshold of activation. So if you make a graph of rainfall against river flow, you see that this graph is, or let's say, if you make a graph of storage versus river flow, this graph is not represented by a straight line. In the linear reservoir, if you make a graph of storage and river flow, you have a straight line, because storage WT is given by the product of the constant K times the river flow. So it's a straight line. And a straight line, in fact, it's a necessary condition to say that the model is linear. In this case of what you see on the screen, if you make a graph of the storage and river flow, it's not a straight line. Okay. Do you have any question? Okay, no, because I got that a micro was opened. So this model is non-linear, and this is why it's called the linear reservoir. And also keep in mind that, being the model non-linear, you can set up a whatever relationship between storage and discharge. So it can be squared. For instance, the discharge may be proportional to the square of the storage. And then you have to introduce the different thresholds to regulate the activation of each discharge. What is the benefit? The benefit is that you are introducing a more flexible model. What is the disadvantage? The disadvantage is that, being nonlinear, it's very unlikely that you succeed in making an analytical integration for it. And therefore, you know, there are benefits and there are pros and cons. And of course, if you need a more flexible model, you can use a nonlinear reservoir. The reason why the linear reservoir is more used is precisely the fact that it's more tractable from an analytical point of view. Okay, this is a brief mention to the nonlinear reservoir. This is something I may ask at the exam, like, can you please explain what is a linear reservoir, nonlinear reservoir, and what is the difference with respect to the linear one? Okay, at this point, I would like to make an application of the linear reservoir. Before we go to the next model, which is called, as you see here, the I-mode model, which is a bit more complicated. It's a very exciting example. It's a second example, which shows that with little more complication, you can obtain a model that is more flexible with respect to the linear reservoir. But before doing that, I would like to make an exercise because I think that by making an exercise, you understand how the numerical integration works. And also you can see with your eyes the limitations of the linear reservoir. And in fact, the exercise is developed with real world data. And in order to get the data, let me go back to the page of our course, which is here. And if you scroll down, after the exercise of the flow duration curve, you get the exercise application of the linear reservoir rainfall runoff model. So, and you see that you have two more links in the lines below: mean area rainfall and evapotranspiration, and river flow data. There are also observed river flow data. We don't need observed river flow data to apply the linear reservoir, but these are given here for the sake of comparison. So we want to compare how the model performs in reproducing observed data. Okay, good. Now, let's first click on the first link, which is the text of the exercise. I click on it, and then I get a PDF. Let me open the PDF. Okay, here there is still written subject advanced hydrology. Sorry for that. I will make a change here. And it's an application of the linear reservoir, as you see from the title. In a catchment, I'm reading whose area is 1214 square kilometers. Rainfall data have been observed at hourly time scale for a period of 1 year. So hourly time scale, which means that we have 24 times 365 numbers. The related observation can be downloaded at these web addresses, which are, we have already the link in the previous page, so we don't need to look at these addresses. Now, by assuming that the runoff coefficient is equal to 0.5, so there is an assumption here, okay? To compute net rainfall, you just have to multiply the gross rainfall by 0.5. Okay, it is required to model the rainfall runoff transformation for the catchment by applying the linear reservoir method. Note that evapotranspiration data are included in the above file, which are not necessary to apply the linear reservoir. They are not necessary because we take a runoff coefficient of 0.5. So from this data here, the first link, the upper one, we take only the rainfall. Good. Now, let's close this and let's click on these two links below, mean area rainfall and evapotranspiration. Now, you see that you get a text file. There is written, the first column is hourly rainfall in millimeters per hour. The second is hourly evapotranspiration. They are synthetic hourly data for 1 year. Okay, it's synthetic, sorry. I thought it was real world data, but it doesn't make a difference for the purpose of our exercise. Okay, good. Now let's close it. Oops, sorry. I closed the whole web page, which was not a smart move. Just 1 second. I'm just going again here, and then here we are. Let's click on the second link, river flow data. You see a river discharges in cubic meters per second, and then we have a column of hourly river flow data. Good. Now, let's open an instance, a session of RStudio. So I go back with this. Sorry, before opening RStudio, let's save these two files on your PC. So instead of clicking over the link of mean area rainfall and evapotranspiration, right-click and save it in save with name. You should get a chance to save the file, and then if you right-click it, you may save it, for instance, on the desktop. I'm saving it on my desktop. Good. Now river flows. I right-click, save file with name. I save it on the desktop. Good. Now we can open our instance of RStudio. Let me find it, because I always forget where it is. Just 1 second. Here it is. Okay, here is my RStudio, and now in RStudio, given that I put the files on the desktop, let's set the directory, set the working directory in the desktop. Choose directory, and I put my desktop here. Good. Now let's open a new script. File, new file, R script. So we can save the script, and maybe if we are happy with the script, I can make it available on my website. Okay. Now let's go to the console and clean it. Okay. So there is a first thing that we have to do, which is uploading data. Good. Let's upload them. So we may call, let's start with the river flow because it is simpler. So let me write a variable, let me assign a variable. Oops, sorry, let me write on the script window. Let me assign a variable river flow equal to what? There is a function in R that we can use to scan input files if they are text files. Look, there is also an option here in the menus to bypass this, because I am using the console to input the data. You can also input the data to the program through the menus, but I am bypassing this step because I prefer to use the console. I think the menus it gives to you a window that it's not very easy to manage in some cases. So I prefer to bypass it and use the console. So the instruction that I have to use, it's called precisely scan. And so scan, and then I need the file name between commas. You see that when I wrote scan, I get from RStudio an help, which tells me what are the possible arguments of the function that I may give. So let's put the file. And I don't remember what was the name of the file that I saved. I think it was river flow. Let's see. I try to put RI, first 2 letters, and then use the tab, no matches. So I think it was, then let me just check what is the name. Here it is. So the name was discharge. Okay. So let me go back here. It was discharge. Let me use the tab to complete it. Okay, good. So, and now let me skip the first line. Why? Because if you remember, the first line was a heading, a line of text. Now let me run it, and you see in the console that we read 8,760. Let's make a check here. what is the product of 24 times 365? I went to the console because this is a check that I don't want to put in the screen, in the script. Yes, you see that indeed the number of items that were read, it's matching my expectation. Very good. Okay, now we have the river flow. You may let's go back to the console. Let's plot it. Plot river flow. I'm using the tab to navigate and type line. Why I'm making this plot? Just to check that everything works fine. Very good. These are our hourly rainfall data. You see that it's a very good hydrograph. It's well behaving. Okay, perfect. Now I can go back to the script and let me upload rainfall. So let me write rainfall. It's equal to scan. Now there is the file rain evapocint. Here it is. How many lines should I skip? I don't remember. Let me go to the file and see it. Okay, sorry. Here is the file. I use a text editor to open it. Okay, only one line I have to skip. Very good. So I can write skip equal 1. Okay, oops, sorry. Now let's run it. Good. I uploaded. Sorry, I want to save the file. Okay, I want to save the script. Let me save it in the desktop, and the script let me call Linear Reservoir. Sorry, Linear Reserve.r. Okay, good. Now, here I have a complication because I have to reject the second column, evapotranspiration. I don't need it. How can I delete the second column? First of all, what I uploaded and called with the name rainfall is a vector. Let me go to the console. I show you the first 10 items of this vector. And you see that there is an alternation between rainfall, evapotranspiration, rainfall, evapotranspiration. I can recognize it because rainfall can take value 0. Evapotranspiration, it's the same value every day and it's different from 0. So I need to remove these values of evapotranspiration. How can I do that? Good question. I think the best way to do it is to transform rainfall into a matrix where the first column is rainfall and the second column is evapotranspiration. And then I will remove the second column. So let me transform rainfall into a matrix. Rainfall is equal to array, and the argument is the same vector rainfall. So I am substituting the vector with an array, and the dimension is two columns, or yeah, and let me see. Let me do this in this way. The dimensions are 8,760 and 2. Okay, 2 columns and 8,000 rows. Perfect. Now, let's see what we obtain in the console. I clear it. I'm clearing the console with Control L. Let's see what we get now if we make rainfall and we make 1, 10, 1. What I'm doing here, I am visualizing the first 10 elements of the first column. Why I am doing this? Because I want to make sure that in the first column I have rainfall. Let's see what I get. This is not good because we made a split that it's not correct. We should have given we should use the transpose matrix. So let me transpose it. I go to the script, rainfall equal T rainfall. T means transpose. Okay, now let's look again at the matrix. It's 1, 110. Still, it's not correct. Okay, so let me do like this then. Let's correct the script in this way. Actually, I'm now working on the script. What I should have done is to invert the dimension of the matrix. In this way, it should be correct. Now let's rerun these two lines. Good. And now let's remake the check. Okay, now it's correct. And if I get the second column, this is evapotranspiration. Very good. Now, students, keep in mind one thing. What I did here at the beginning was to make a mistake. And then what I did is a mistake. Why? Because the dimension that I gave for the matrix, which was 8,000,2, was not correct. What I have to use is 2,8,000. Now, how could I realize that I made a mistake? By making a check in the console. And then once I noticed the mistake, I went back to the script and I changed it. And I ran it again. And then I made a second check, and now the check is fine. So this is something that I did, let me say, not really on purpose, but I think it is useful, because I hope that you followed me in the process of writing the code, checking the code, resolving the mistake, rerun the code. This is something that it's important that you get trained to, because today we are doing a different thing with respect to last time. Today we are writing the code from scratch. We are not using a pre-cooked code, which means that we may make mistakes because the code that we are using was not checked in advance. And then it's important that we learn how to make tests, how to recognize mistakes, etc. Okay, now let me go back to the script. I have to keep only the first column. So rainfall is equal to rainfall 1, comma. Let me run it. And now if I go to the console and I put rainfall 110, I have only rainfall here, which is what I wanted to get. Let's plot it. Plot rainfall type equal line, just to make another check. The plotting is an excellent way to make another check, and this is rainfall. Good. Perfect. Okay, now let me clear the console, and let me say one thing. I may here apply the rational formula. Just to give you an example of application. The rational formula, we can apply it because we know rainfall. Because what is this rainfall? It's daily rainfall. So it's daily rainfall intensity. Okay. When you get rainfall depth in one day, if you divide this depth by the time 1 day, you get daily rainfall intensity. Very good. What is the unit that we get? So, sorry, this is not day, is hours. So what is the unit that we get for rainfall? Is, remember, it's written in the file, millimeters per hour. Okay. So given that we have the runoff coefficient and we know the area of the catchment, which is 1214 square kilometers, it's very easy to apply the rational formula. We just have to be very careful about the units. So let me try to make this computation in the console, not in the script, because now we are doing something that it's not related to applying the linear reservoir. We are just doing an experiment. So let's make it in the console, and let's define a variable which is river flow. We can call it river flow CEA. Okay, and this is equal to what? It's equal to rainfall. Or let's put first the runoff coefficient, 0.5 times rainfall. Rainfall, it's called rainfall, but given that I want to get the river flow in cubic meters per second, I have to be careful of the units. Rainfall is expressed in millimeters. So I have to divide rainfall times 1000 to put it in meters. And then I have also to put it in seconds, because this is the time step is 1 hour. So in order to put it in second, I have to divide times 3600. I think in this way it is correct. Let me, yeah, I think so. But just 1 second, because it's, yeah, I think it is correct. It is correct, yeah. Then let me think if it is. I think it is correct, but I'll make a check later. When you work with the units and the conversion factors, you have to be very careful, because it's very easy to make mistakes. And let me just write on a piece of paper. I want to make sure that, because if I have 10 millimeters per hour, okay, I need to divide by, yes, by 1000, but it's, and then I have to divide by, yeah, I have to divide by, yeah, it is correct. Okay, I think it is correct, but we will make a check. And then we have to multiply the area of the catchment. Is 1214 square kilometers. I have to put it in meters. So 1, 2, 3, 1, 2, 3. I think this may be correct. Let's try. And in order to check if it is correct, let me make a plot. Okay, and the plot is plot of river flow 1. Type line. Okay, sorry. It's river flow, it's not 1, is CIA. I think the order of magnitude, it looks okay, because let's make a plot of the observed river flow. And so plot river flow, type line. You see that the, yeah, it's not really, the order of magnitude is a bit, but I think it is correct, because you see that the hydrograph is very different, looks very different. And this one, it's more spiky. And then being more spiky, I think it's being more spiky, I think it also shows very high maximums. So I would say that what we did is correct. Okay, now let's make a comparison of observed versus simulated. So plot river flow and river flow CIA. So here I'm plotting the observed river flow against the simulated one. Let's see what happens. Yeah, you see that it's indeed it's not a good simulation, because it means that the rational formula doesn't work really well. And because, you know, if we expect similar values, and the values are very different. So if similar values means that this plot should lie on a straight line. The observed values are very different with respect to the simulated. But this is fine, I mean, because I'm not expecting that the rational formula works well. Now let's see if the linear reservoir works well. Okay, works better. Okay, in this case, I mean, it's not really the best. Okay, now let's move forward with the linear reservoir, and then I go to the script. Just 1 second, because I need to make reference to 1 second in order to. I need to make reference to a code that I already had prepared, because I want to make sure that the units are correct. Okay, so we can start with the linear reservoir, and what we can do is first of all define a variable of the output. So, and the variable of the output is, let's say, we can use, for instance, river flow. Oops, sorry, I'm not writing. River flow linear reservoir, capital LR. And then let's put it equal to 0, or let's say, let's make a vector, repetition 0, 8760. So this is, let me put a blank line here. This is the definition of the vector of the simulated river flow. Now let me define also k, because I need a trial value of the parameter k in order to run the model. And what we can do is to use a value which may be something like 15 times 3600. This is a trial value. I mean, we can change it. Let me start with an initial guess, okay? Okay, now I think we can start with the, let me put here the definition of the area of the basin, of the catchment. So it's 12, 14, 1, 2, 3, 1, 2, 3, because it helps us to work with the numbers. Time step is 3600. Very good. And then there is the number of delta t, the number of time step, it's 8760. Okay. Now, we have to do the numerical integration. Before I move forward, let me know, because I can't see you, if you have any question, please. Let me make a poll, because I wanna, so I take the opportunity to give you a break of 3 minutes. Let's see. Okay. Just 1 second. Okay. Here we are. Okay, let me make another one. Okay, so I want to know if you are making the exercise on your PC or if you are just looking at what I'm doing. And so the question is, are you following me by repeating what I'm doing? So if you are just listening and doing nothing, just put no, it's anonymous. And otherwise, if you are following, if you are repeating, just put yes. So I think it should go to our chat. Let's see. Okay. Good, should be in the chat now. Let's see if it's there. Yes. Okay, please vote. This was my guess, that most of you are not repeating. Somebody's repeating, okay. Okay. You know, it was my guess because when how can I realize if students are following or not? I mean, I can realize it because usually if you are following, my expectation is that you may have some questions because it's unlikely that you can follow me, that everybody can follow me. And yeah, okay, I see, Emmanuel, thank you. Too fast, I see. Okay, I understand. You know, the problem is that I hope that with the availability of the video, I hope that you can repeat the exercise on your own, because I understand that the velocity, the speed may be too high. On the other hand, there is to say that if I slow down, we cannot we cannot dedicate too many hours to the exercise. So if I slow down, it takes 4 hours to complete this exercise, and it is too long, believe to me. And so I think that given that there is the video available, and the video you can stop it, and you can, I think it is more useful for you. It requires an extra effort. It requires some homework, but I think it is more useful for you if I propose more exercises. And look, during this course, I will propose, we already had one, this is the second. There will be a third one. I'm not sure if there will be a fourth. So to give you an idea. So I'm not proposing many. And I think that I count on your patience. I understand that it requires some homework to try to repeat what I'm doing. On the other hand, I think that it's more effective for you. Anyway, for today, I think that we still have 25 minutes. I think we can get to the end, and then let's see. And if you feel that it's not the right way to follow for the next exercise, I can try to be slower. Okay, which means that maybe that we miss one exercise, but on the other end, you can follow better. Okay, now let me go back to the R script. So now I can start the simulation, and I have to perform such numerical integration. Do you remember W0, W1, etc.? And I need, this is to be repeated for the whole number of the time steps. So it is to be repeated 8,760 times. And in order to make it easy, I need a cycle. And the cycle, you may let's write it in this way. You may remember if how to write cycles in not only in R, but also in Visual Basic by using the instruction for. So let me put for E in 1, E in 1, 2, and delta T. Okay. And then I can take a new line and open a curly bracket. The curly bracket, I need it because this for cycle includes many instructions. In order to get the curly bracket, the opening curly bracket, I press the key Alt-GR, which is on the right of the space bar. I keep it pressed, and I press the number 7. So contemporaneously, Alt-GR 7. And here you have 2 curly brackets. Let's put a new line here because otherwise we get confused. And let's write the instructions. Okay. So what I have to do first is to compute the new W. So the new W is WI, or let's say, let's do like this. W is equal to W, which is the previous value, plus rainfall. And rainfall is called rainfall. Rainfall, and I would say that now here we have to take care of the time step. So rainfall and the measure unit, we have to divide it by 1000 because rainfall is in millimeters, and we have to divide it by 3,600. It is the number of seconds in an hour. Okay, and at this stage we have to multiply it by delta T. Delta T is T step. T step. I think to make it cleaner, we let me check because I think there is something in the chat. Okay, and delta T is the number of time step. So the number of time step is 8,760. Okay, and I think that here instead of 3,600, to make it cleaner, we can divide by time step. And you may say, what is the meaning of dividing and then multiplying by time step? I could avoid this. Yeah, it is correct, but I want to make things clearer. So what I do is at each time step, I take the previous value of W and I sum rainfall. And rainfall is in millimeter per second. So I have to divide it by 1000 to make it in millimeters per hours. So I have to divide it by 1000 to make it in meters, and I have to multiply by time step. I have to divide by time step to make it in seconds. And then I multiply again by time step, because if you remember the formula is W1 is equal to delta W is equal to P minus Q times delta T time step. Okay, this is my updated volume. You may say that I am forgetting here to subtract the river flow. Actually, I'm not forgetting. It's the fact that I make the assumption that I don't know it, and then given that I don't know it, I take it as 0. Okay, and then I can compute the river flow now. I can write here river flow LR I is equal to W divided by K. Good. Now that I computed the river flow, I can subtract it from the volume. So W is equal to W minus river flow I times this is in cubic meters per second, which is fine. I don't have to make any conversion factor, but I have to multiply it by time step, because I have to multiply the river flow times the time step to get a volume. In this way, what I did is, at the beginning, compute a new volume by summing to the previous volume the rainfall. Compute the river flow with this new volume, and then at the end, I subtract the outflow from the volume. This is a scheme which is precisely Euler method, because there is no iteration. It's just assuming that river flow is 0, and then after the computation, for computing the volume, river flow is 0, and then after the computation, we subtract to the volume the outflow. Now, here with the numerical approximation, we may get a W that is lower than 0, which we cannot tolerate. So let's put a condition. If W is less than 0, then W equals 0. Okay. Now our fourth cycle is completed. And the only thing that we have to do, it's at this stage, multiply, first of all, just 1 second, here I have to put LR. Okay. And now what we have to do is river flow LR is, we have to take into account the area of the basin, so we have to multiply it by the area of the basin. River flow LR times. Good. Okay, now we are done, and we could run it. Let's see if it works. So I go back, and then let me try to run it. I select it. Let's see if we get any error or any run. Okay, there is, now I understand. I didn't define at the beginning W, so I have to make here W equals 0. It's the definition of W, just 1 second, because it's, yeah, I think I have indeed to do that. And let me see now if it works. Let me run it again. Now it seems that it works, but there are warnings. So let me see what may be the warning. Let's use warnings as R suggests. Okay. Here there is something wrong. Let me see. Okay. Here in rainfall, I forgot to put rainfall I. I think now it should work, because rainfall, of course, must refer to each time step. Now it should work. Let's see. Oops. I have to select again. Finally, I hope that we get something meaningful. Yeah, we don't have any warnings. It seems that is okay. Now we have a vector. Let me clear the console, which is river flow LR. Let's see. Okay. It exists. Let's see what is the max. In this way, we see if it is 500, which is okay. I mean, the max looks okay. Let's take a plot of it. Plot. Okay, type equal line. Yeah, doesn't look bad. Doesn't look bad. Much better than the rational formula. Okay, now what should we do now? We should check if we are happy with the simulation. And how can we check it? By comparing what we simulated with observed flow. That would be an idea. So let me try to do what I did before, like the scatter plot. Plot river flow LR, comma, river flow. Let's see what happens. Okay, you see that, yeah, it's still not very satisfying because if the observed values were equivalent to the simulated values, I am expecting the points lying over a straight line, which is not the case. And but you may say, why don't you compare directly the hydrographs, which is better? Okay, let's do that. And let's do that in the script. So it is directly done when I run the script. Okay, so let's make this plot. Plot river flow LR. Okay, type equal line. Good. But now let me also plot over here the observed ones. Observed one. Lines, river flow. And color equal red. And let's put line width equal to. Okay, now I think the plot should work. Let's try to run it. Let me see what is the reason why it went over the previous plot. So let's close it. Good. Okay, let's remove also the old one because it is keeping all the plots. Let's remove all of them. Okay. We should be almost done. Okay, let's try to run the script again. Okay, there is something which is wrong here. Plot river flow. Why doesn't? Okay, I forgot here an R in river flow. Good. Let's try to make the plot again. And there is only the second line. I don't understand why. Let's see. There is still a mistake in. Okay, I see. I think we need a comma here. Let's see. Okay, very good. This is a comparison of observed river flow, red line, simulated river flow, black line. You see that the comparison is not very good because the simulation is higher than the observed. So what could we do in this case? We are almost done. Let me save the script. So what could we do in this case? And let me clear the console. I mean, we have a way to use the model flexibility. to adapt, to better adapt to the catchment that we are considering. And the way is the parameter k. So I can try to change k. So let's put k higher, okay? Instead of k 15 times 3,600, let's put 25. Let's see what happens if we increase k. What happens if you increase k? Remember that the outflow is given by storage W divided by k. So by increasing k, I am expecting to reduce the outflow, which is precisely what I want to get here. The outflow, the red line, the black line, the outflow, the black line, is too high. So let's try to reduce it by increasing k. Okay, good. We have already the code prepared, so we can rerun everything. So let's select everything and make run. So this is the new graph. The new graph is a bit better, but still the black line is too high. So let's try to increase again k. Let me go here and let's exaggerate 50, sorry. Okay, let's see what happens. We are getting closer, let's say. Let's try to again increase k, 100. Run. Okay, I think we have to increase again, but we are getting close, you see, not bad. So let's go here and let's put 200. Remember, changing k is perfectly reasonable because we are trying to use the model flexibility to adapt the observed and simulated hydrographs. And still, I think we can increase k a little bit, but we are getting close. And let's try to put 300. Maybe it's too high. Yeah, we are. I don't think we can do much more than that. And you see that it's not bad, but still, I think we should work on it some more. And let me just show you the scatter plot. Plot river flow LR river flow. Let me see. Okay, here it is. You see the scatter plot. It is closer to a straight line, but still it's not very fine. But it's much better than what we got with the rational formula. So if you remember, what we got with the rational formula was not good at all. And here it's not bad. If you run again the script to get the previous graph, it's not bad. Okay, so what we can do now, just to close up, is to work on the script a little bit more and to put some comments. And then I make the script available to you. So I think that here, for instance, we may put a comment, upload of the river flow, observed river flow. And here, let's put upload of observed rainfall. I forgot to put the hash here. Upload. Let's make it simpler. Okay, and then here, eliminating the column of evapotranspiration, and let's put it here. And then here, definition of vectors. Let's put it here. Definition of vectors and input data. Or let's say, yeah, input data. Okay. And then here we can make start of the cycle, of the computational cycle. Cycle. Let me see if there is a, I think this is self-explaining. And then let me just put a comment here. It's rescaling to the catchment area. And then here plot of the output. Okay, and let me just put here, this is a tentative value for K. Tentative value for K. Okay, I think we are done. Now, it's 10:44, so we are close to our end of the lecture. Let me just summarize. We wrote a code for the application of the linear reservoir. What are the key issues that you should try to resolve today if you didn't resolve them already? First, there is the technical writing of the code. I think that probably you couldn't follow me because I was too fast in explaining several instructions that you still didn't know. So this is just a technical issue. I think that if you repeat it, you don't have any problem. The second issue is the numerical scheme that I adopted here. Okay, this is an Euler method. It's slightly different with respect to what I adopted on the graphic blackboard at the beginning. It's slightly different. You may also change it and apply the scheme that I summarized on the graphic blackboard at the beginning. It's no problem at all. And it's anyway an Euler method because there is no iteration here. I'm not guessing any value, and I'm just moving forward step by step. And what I do is to subtract the river flow after the at the end of the time step, after I computed it. So there is a numerical approximation, and try to understand the rationale behind this scheme that is selected here. And this is the only issue, conceptual issue, that you may need to resolve regarding the lecture of today. Okay, and today we concentrated on application. So again, I don't ask you anything related to numerical integration at the exam, but I mean, given that we are at a degree program in engineering, I think it is highly advisable if you had some issues today that you resolve them. If you have problems, I can make myself available to repeat it for those students that couldn't follow and cannot resolve it through an homework. You just have to let me know. The only thing that I would ask you in that case is that we don't use lecture hours. So I'm willing to make an extra teaching to repeat the exercise step by step. If you prefer, you just have to let me know, and then we can find let's say 1 hour and a half in a day when you are free and I am free to repeat it. No problem. Okay, and I'll make this code available on the website. You will find it starting from, I would say, tonight. So if you want, you can repeat it entirely. But there is to say that you have the video, so you can repeat it anyway. Do you have any question? Let me just check. Yeah, I saw. Just 1 second. Yeah, it is saved. Let me see the question and let me share the screen. Let me just let me get the question. Okay, isn't it unrealistic to consider a whole base in having the same response time? Yeah, it is unrealistic. And let's say, let me. Okay, yeah, it is unrealistic. And it is unrealistic also the fact that you consider rainfall uniformly distributed. You have only a rainfall value, but usually in the mountains rains more than in the lowlands. So basically we are using what is called a lumped model. What is the meaning of lumped? It means that the catchment is treated as a unique entity. And our control volume is the whole catchment. So for sure it is unrealistic. And this is why, even if we changed the parameter many times, we couldn't get a good simulation of the output. And your question is very good, because the next steps that we will make on Monday is to study a model that allows to take into account these differences, these spatial differences. And it allows partially to take it into account. But it is correct what you say. Yes, it is unrealistic. And this is why we can't reproduce the observed values. But keep in mind that whatever complex model you use, it's like with climate models, they are always an approximation of the reality. And therefore, environmental models, they are always an approximation. They cannot lead to a perfect simulation. And the reason is that some processes and some variability in this case, as you mentioned, it's neglected. Other questions? Okay, good, students. I'll upload the video today in the afternoon and the code today in the afternoon. Thank you very much. Enjoy your weekend, and let's meet on Monday, 9:12, starting from 9:15. Let me see the new message. Okay. Thank you very much for your patience today. I know that today was a bit tough, and the only thing that I repeat to you is don't worry for the exam. But I want to give you opportunities to get skills, and you know, to maximize your opportunities, I need to go a little bit fast. But as I said, if you want, we can repeat the exercise. Thank you, and enjoy the rest of your day. Ciao.